Hello and welcome to Lesson 1, Part 3. So last time we talked about notations and mathematical tools we will use later to describe and analyze neural networks that we're going to make. But we need a high-level framework for starting to talk about what we're going to do with neural networks. A neural network is a type of learning machine, but we haven't yet even addressed the question of what is a learning machine. And that's going to be today's topic. We're going to talk about what is a learning machine, and what framework are we going to use to approach training them and understanding them. Let's give a quick definition. A learning machine is any machine or algorithm that has a set of internal states or variables that are adjusted to raise performance on a given task in an objective fashion. This definition is intentionally vague and can be applied to a vast number of algorithms and machines. Let's break it down further into its core components. A learning machine takes inputs from an environment and uses some parameters to decide how to react to those inputs. We also need a method to determine if that reaction is appropriate given the inputs for the task we're trying to get our learning machine to accomplish. And somehow, using the knowledge of how good or bad our learning machine was at the task, we need to update the machine's internal parameters to try to make it better at the task. Let's take a look at a simple diagram of a learning machine. This is a schematic diagram of a learning machine. Here, the machine itself is represented as a box. It takes some inputs we often call S. It uses some parameters on the inside of the box, often called W, and it outputs a response that we will often call R. In this way of looking at things, we usually know what the desired response is given a particular stimulus, and we need some method to compare the actual response compared to the desired response. And again, we need some way to use this comparison to change the internal parameters of W. This forms a very elementary feedback loop. In this way of looking at things, the machine itself and its inner workings can almost be treated as a black box, as we're not particularly concerned about what's in it. In fact, from some theoretical perspectives, we only really care about the exact method of comparing the response and the desired response. In practice, though, everything inside the machine matters, and everything that comes before the machine and the environment matters. So here's a little story to help you remember those letters, because we're going to see them frequently in these lessons. S is for stimulus, W is for weights, R is for response, and O is a magical oracle that just happens to know what the correct response is given any input. Before we can figure out how to even adjust the internal parameters of the machine, we need a precise way of comparing the actual response to the desired response. We need to know exactly how bad our algorithm is doing, based on some criteria about what we think is important in the task. This leads us to the objective function. An objective function is an objective way of measuring the error between the actual response of a machine or neural network and the desired response. Usually, it's conceptualized as a distance from the desired response. This means that when the value of the objective function is high, the machine is far away from the desired response. It's performing poorly. But when the objective function is small or has a small value, the machine is very close to the optimal performance as defined by the objective function. Okay, let's talk about the basics of what an objective function looks like in the field of neural networks. Usually, an objective function is a scalar function that takes the parameters as inputs. In our field, the objective function is usually denoted as L of n, or L subscript n. In our field, we don't use ln for natural logarithm. Whenever we want to use natural log, we actually just use log to mean natural log, as log base 10 rarely comes up. Okay, now let's take a look at one of our favorite objective functions for changing the parameters of a neural network that has linear outputs. This objective function is called the sum squared error function. It's got several other names, such as the mean squared error function, and is highly related to the field of statistics. For people familiar with ANOVA and other statistical methods, it should look a lot like a sum of squares, and it should also look almost exactly like a Euclidean distance metric. There are n pairs of stimuli, S, and desired response is O. In this equation, I acts as an index over the pairs of stimuli and desired responses. O and R are vectors indicated by their bolding. Further, they are column vectors by default. In typical neural network notations, the square here means something a little bit unusual. Here it means take the resulting vector of O minus R and transpose it and multiply it by itself. In effect, this means take all of the elements of the vector O minus R, square them, and then add them all together. So in essence, this objective function is a sum of all of the squared differences of all of the outputs and the desired outputs, and over all of the stimulus patterns. We're going to see this objective function many times in the future, but right now, let's just ask the simple question of what does an objective function allow us to do? Imagine a learning machine that only has one parameter w, and we've defined some objective function that takes that parameter as an input. We could make a graph of where the objective function value would be for every value of our parameter, just like this. The lowest point on this curve is called the global minima. Our overall goal is to try to reach the global minima, but in practice, frequently all we'll settle for is just reaching one of the local minima, which is any of the bottoms of the valleys on this curve. This might seem like a trivial task, and for a one-parameter learning machine, it really is. But we need to develop methods that can find global and local minimas in very high-dimensional spaces. A typical learning machine could easily have millions or billions of parameters. And human beings are really only capable of looking at a graph of maybe 3 parameters. Further, trying to sample a graph for even 1,000 or 10,000 dimensions proves computationally intractable, so we need methods that will work even when we can't see where we're going. To illustrate this problem, consider the graph of ln of w. Imagine we generated this curve by sampling it 100 times. Evaluating ln of w 100 times is not that big a deal. But imagine if we wanted to have 2 dimensions and we wanted to sample each of them 100 times. Well, unfortunately, that means we're going to need 100 times 100 samples, because they will form a grid of possible positions across W1 and W2. 100 times 100 isn't too terrible, but it is rather large. It's 10,000 samples. Imagine if we further wanted to have 3 input variables, or 3 parameters. As you can see, the equation for finding out the number of samples is the number of samples across each dimension to the power of the number of dimensions. In an example with 3 input parameters sampled 100 times each, we would unfortunately need to generate 100 to the third samples, which is 1,000,000 total samples. In our field, a learning machine with only 3 parameters is downright tiny. We are typically dealing with learning machines that have anywhere between thousands of parameters and millions to billions of parameters. If we only had 1,000 input parameters, the number of samples we'd need if we sampled each dimension 100 times would be 100 to the 1,000th power. Just to comprehend how big that is, that's a 1 with 2,000 zeros following it. It is so large that we have no hope of computing that number of samples of anything before the heat death of the universe, given current technological limitations. 100 to the 1,000th power is greater than the number of atoms in the universe, which is only 10 to the 80th power. Because of this insane growth, we need methods that don't require us to sample even small regions of high-dimensional spaces. So let's talk about some alternative methods for searching for local minima. One possible way to search for local minima is to simply randomly select a point in W and keep selecting points until you find an acceptable local minima. Let's look at an example of what it would look like to run that algorithm. Notice how the point keeps getting nearby one of the local minima, but it never settles into any of them. Further, each step is equally likely to move away from the local minima as it is to move towards the local minima. If we run this algorithm for all of eternity, there is actually no guarantee that we will find either of these minima, or that we will settle on any minima at all. In practice, it's really unlikely that we will ever find any local minima using this method, and for high-dimensional spaces, it's unlikely that we'll ever find any good region of the space for complex problems. Given these problems, it's safe to say that the random selection method is a poor method for trying to find local minima in an objective function landscape. Let's imagine a slightly different method for trying to find the local minima in this graph. Imagine if we select random points within a window around our current point, and then we update what our current point is if we find a point that's lower than our current point. But if we don't find a point that's lower than our current point, we throw it out and we return to where we were. Let's run this algorithm for a little while and see what happens. Notice that we get really close to one of the local minima and we stay close to it for the rest of eternity. This algorithm actually produces fairly decent results and will generally move downhill. It will, to a degree, optimize our network. Unfortunately, it turns out that it's pretty bad at moving downhill. It's not the most efficient. And it also has a bad habit of getting stuck in particular local minima. However, we can actually adjust this just a little bit and produce one of the more powerful machine learning algorithms used today called simulated annealing. All we have to do to get simulated annealing is add some small chance of going uphill rather than downhill, and then what we do is we lower that chance over time. We'll talk about simulated annealing another time. Right now, we're going to switch to talking about the current method that's typically used in training neural networks today. But please understand that simulated annealing is actually a very effective method at training many hard machine learning models. Simulated annealing is really slow. The reason for this is that in a high-dimensional space with possibly millions of dimensions, you will randomly go uphill far more often than you will go downhill. And in fact, you will typically not go downhill in an efficient direction. You will probably meander downhill very slowly. Imagine for a second that you're a blind man on a hill, and you want to go downhill. Really, the only thing you have at your disposal is the slope on the hillside that you're on. In math, we call that slope the first derivative. If we have a smooth and continuous function, that derivative is defined for all places in the parameter space. Further, if we know which direction is downhill, we can know for certain that we are going downhill as fast as we possibly can. We're not wasting our updates. This method is called gradient descent because the first derivative of a function that only has one output but could have any number of possible inputs is called a gradient. Now, in order to make it gradient descent, we actually have to move in the direction opposite of the gradient. The gradient will tell us which direction is uphill. The negative of the gradient will actually tell us what direction is downhill. So let's look at our example and apply this update method. Notice that without delay, it starts moving directly towards the nearest local minima, and as it approaches the local minima, it slows down and approaches it more precisely. This algorithm is actually guaranteed to converge to the nearest local minima when certain constraints are met. Further, with some extensions, you can actually make gradient descent formulas and equations and update methods that are guaranteed to converge to the global minima, again when some constraints are met. Frequently, it will be very hard to meet those constraints. Gradient descent has proven to be one of the most powerful machine learning techniques for training all manner of neural network algorithms. It has in fact been unreasonably versatile. In many ways, the framework of using objective functions, also sometimes called empirical risk functions, and then doing gradient descent or gradient descent-like updates on them is really the start of the modern framework of neural network learning and design. Before the introduction of empirical risk functions and objective functions and notions of gradient descent across parameter spaces, generally speaking, every neural network had its own unique handcrafted learning rule, and unfortunately these rules didn't really generalize well to other architectures. This meant creating new networks and new neural architectures was actually quite difficult. This inability to create new architectures did in fact stifle the field for quite a time, and severely limited what types of architectures were possible. In fact, before this framework was introduced, training neural networks that had multiple layers was all but impossible, which is unfortunate because one of the hallmarks of the recent boom in neural network research is the use of many layers in neural network architectures, or deep neural architectures. I think that's about it for this episode. In the future, we're going to focus on learning how to take the derivatives for these complex neural networks and architectures that we're going to learn about. Understanding how to take the derivatives so you can implement the update rule for gradient descent for arbitrary neural networks is actually going to be one of the core tools you will need to learn to better understand this field. And unfortunately, that's why we're going to need to introduce things like matrix calculus and array calculus. Hopefully the notations that I am creating and will be showing you will be helpful in making these new types of math accessible. Understanding how to take these derivatives and do this type of math is actually the core bit of knowledge required to move forward in this field and feel secure in your ability to understand what articles and texts in the field are talking about. Unfortunately, learning how to do this math seems to be one of the hardest things to do given the lack of resources around it. So I will be paying special attention to trying to teach you how to do this math.